Hello folks, welcome to my channel. My name is Dan Delamarski. I'm a product manager and engineer. I do a whole bunch of random stuff on GitHub and on my blog, and this video is in relation to one of these random projects that I just built for the fun of it, which is reverse engineering a Stream Deck. And before I go into any of the details, know that if you're a beginner, you've never reverse engineered a device, there's no knowledge that you actually need to know ahead of time to enjoy this video, because in addition to this, I also have a blog post that you should check out, the link in the description, to learn more about. And if you go there, there's all the details. It's much more in depth. This video gives you a very surface level overview. But nonetheless, let's get started. And to get started, I just first want to show you what a Stream Deck device is in case you don't know. And it's this collection of fancy buttons. And what this collection of fancy buttons does is essentially you can use it as a tool for shortcuts, right? So if you want to launch an application or control your multimedia, if you're using OBS Studio for streaming things, or what I do right now is to actually record this video, I can use the Stream Deck device to manage it. So when I was thinking about it, I was thinking, okay, well, I've never reverse engineered it. I've never actually used anything like this before, and I had no idea what's inside. And as I was thinking about it, I realized that because it's a USB device, it connects to a USB port, a universal serial bus port on your computer. I could probably analyze the traffic that goes between the device and my computer. And the fancy thing about this device is that it's a HID device, or a human interface device. And I guess HID device is kind of redundant because the D at the end stands for the device. What this means is just a fancy way of saying that it's a device that connects to your computer that accepts input and allows for some kind of output potentially. And basically it interacts with humans. That's what it is. There's tools that are built for any platform, whether it's Windows or Mac OS or Linux, that allow you to inspect the traffic, the bits that go through the wire from your device to your computer, from your computer to your device, if that is ever the case. So one of these tools is Wireshark. So I'm just going to jump over to my screen here, and I'll show you how this works. So Wireshark, it's a open source free tool that you can download today. And what this tool does, it's mostly used by folks that are doing network analysis. So they are analyzing the traffic that goes to their machine. For example, if you're debugging a web application, or maybe you have a client application that you want to inspect the traffic that it sends over the wire, you would use something like Wireshark. Now, the beautiful thing about Wireshark is that it also has another component that comes bundled with it. I believe it's developed by a different team, but it's bundled with Wireshark for Windows, Mac OS, Linux. It's called USB PCAP. USB PCAP stands for USB Packet Capture, and it's a tool that comes bundled in that allows you to capture packets not only on the network, but also that are going between USB devices. So here on the screen, you see an example of a Wireshark home screen. So if I wanted to capture the data that happens on my network, I can look for these local area connections, or maybe I have the Wi-Fi. But notice that there's also these USB PCAP options. These allow me to inspect traffic that happens to go through the USB protocol on the wire from all the devices that are connected to my computer. So if I wanted to look at what my keyboard is sending, or what my mouse is sending, or maybe, there's a device that captures the video stream from this camera that I'm filming this right now, I could use this tool and look at USB PCAP to get that data. Before this video, to make sure that you're actually not as bored watching me do this, I captured a whole bunch of example packets that are happening between the Stream Deck, and it kind of describes my logic for how I analyze it. So first of all, I plugged in the Stream Deck into my computer. Then I used the USB PCAP interfaces here to try and really guess where it happened to be connected based on the USB hub. Now, on a given computer, there's a bunch of potential USB hubs you can have. So it's a little bit of a trial and error. And if you go to the folder where Wireshark got installed, you can use the USB PCAP tool in the command line to list all the available hubs and connected devices, which would make it a little bit easier. And I'm sure as I record this video, somebody will figure out a command that allows you to just list all the devices and the exact hubs through some command line parameter that I did not know about. Please leave it in the comments so that I can learn with you. But I have these things captured here, and I'll show you what I do and how I then formalize this into the library that I'm running. So I have here a file that's pcap.ng. So this is just a capture snapshot for what I already captured when I was analyzing my device. And notice that as I was looking at the Stream Deck again is this button box here, as it was connected to the computer. What I used to do is I used the software that comes with it, and I tried to replicate what it did. So I would, set up a button that does sleep, and then look through the USB logs in Wireshark to see, well, when I ask Stream Deck to sleep, what exactly happens? And there's a lot of ways in which HID devices interact with your computer, and main of them is being through reports. There is input reports, output reports, and feature reports. And again, if you go to the blog post that I will link in the description, you can learn more about those. In Wireshark, it's very easy to look at those reports and look at the source of that, which in this case, you look at this address, right? 220. This is not the IP address. This is actually the pointer to the exact hub, the device, and then the actual, I believe it's called the report address that you are using to connect and talk to the device, right? So it's very static when the device is connected to your computer. So in this case, I have, for example, 220, and I see that this came from the device to the destination to the host. And the host in this case is my computer. Well, I actually want to see what my computer is sending to the device, for example, when I try to make sure that, I set it to sleep because I press a button on the Stream Deck that does sleep. So I would look at host 220, and then I would look at the setup data. So this gives me some information about what it's doing and setting configuration, but this is kind of pointless here because it's just setting the configuration. So what I actually want to do is look at set report, because remember I mentioned that HID devices, or I guess again, very redundant, it's a human interface device. Look at the host to the address, and then it goes with a set report, right? So there's a request here. And when I started looking at those, that's exactly what I used as a starting point. So my host, my computer, is talking to the device and saying, hey, here's the data that I'm sending over. And this is the data that you can analyze through a hex editor or a hexadecimal editor. I have this data here for the report. It's built in hexadecimal, so you should get a little bit more comfortable with that, but it might take some time. But as I was looking at what the host is sending to the device, so my computer sending to 210, I looked at the data fragment and I noticed that, okay, this is 0308, and there's a bunch of other stuff. And I just started analyzing what's happening. So when the host would send data to the device, what data is it sending? What kind of information? So for example, here's a different set of packets that shows 0207. And all I started doing here is just looking for patterns. Like the easiest way to start reverse engineering something is when you're looking at the data is to do the same thing over and over, or to do slightly different things over and over, and then look for patterns. So what I did here is when I was looking at things like, I would press the sleep button and try to look and see what the device is doing and what kind of packets it's sending, right? So I would look at the expansion here and see that there is something that says, I look at the data fragment, that's the interesting part. And then I'd see, okay, 0308 and then 50,000,000. And then when I would set the brightness of the device lower or higher, because that's what the Stream Deck software did, I would then look at what changes here. And the value that changed, for example, would be this 50, which is the hexadecimal representation of the actual brightness value that goes from the range of 0 to 99. And remember that because it's hexadecimal, I need to convert it. And I noticed that the 0308 would stay the same. So these are kind of clues where I can then infer and say, okay, well, 0308, that likely is the header, and then 50, and then it would say go to 01, 02, 03 are likely values that are representative of the brightness. And I would not really be too encumbered by everything that follows at the end, right? Now, there's things like length that I would look as well and say, okay, well, this is 32 bytes. So if I would try to replicate and send something to the device, it would probably be 32 bytes to make it go to sleep or change the brightness. And so I would try to recreate those packets with my C# application because I was writing it in C#. And so this is an example where 0308 would be the header to change the brightness, then 50 set the brightness on the device. And then there would be other things that I would also do is because I wanted to set the image on the Stream Deck for a given button. Well, how do I do that? Okay, well, it's going to be a slightly different approach because there's different kinds of packets being sent, and it's a little bit more complex. And again, read the blog post because I explained this a little bit more in depth. But when I would look at the packets that are being sent, so I would go again from host to the device. When I try to set an image, set an icon, I would look and notice that the packet data length for the HID is 1024 or 1024 bytes. And then I would look at the patterns that exist here. So for example, 02, 07, 18, 01, 6F, 03, and all these byte patterns. And as I started setting those images over and over, I started noticing that, for example, 02, 07, they're consistently the same. So, okay, that must be a header that sets an image. Then there is the actual button number. For example, if I set the image to the button number 18, well, the 18 would show up there. Or I guess it's in hexadecimal, so I'm not converting it correctly. But then there would be different values here where would be 01 that I couldn't necessarily tell what 01 is. So let me just jump to the code for my SDK. I will show you exactly what is happening and how all this Wireshark goodness maps to the things that we're talking about. So we're looking at the SDK here, and this is the .NET implementation of my Stream Deck code that talks to the Stream Deck. So if I look at, for example, a connected device, this is where I'm looking for the exact device that is connected to the computer. This is one of the Stream Deck models. And I have the method here that's called setKey, which will set the image on the key, which you pass it a key identifier and then a byte array. So an array of bytes, just like you see here. And then you pass it an image, right? So this is representative of some JPEG because apparently that's what the Stream Deck supports. So what the C# code does is it does a bunch of fancy things, or fancy looking things that are not that fancy, but like I said, it starts with the header, right? So 0207, I don't actually know what they mean, right? Like Stream Deck, the folks at Elgato decided to do that. That's great. But I looked at the header and said, okay, 0207 seems to be consistently there when I try to set an image. So, okay, this must be a header. Then the next is going to be the key ID, so the identifier for the actual key that I want to set this. So for example, if I want to set the key number 1, I'd pass the identifier 1. Finalizer, this is where I realized that sometimes the images would be split. So if I try to set an image that's a little bit larger than 1 packet, so remember here, packet data length is 1024. What would actually happen that a second packet would be sent with the same header, it would be 0207 button number. And then if the packet was final, the value would be 01. If the packet was not final, the value would be 00. And again, I only inferred that once I started looking at sequences of packets of what would actually be happening. Now, there's the bit mask length and shifted length, and this is a little bit trickier. And this is where the trick that you see here, I learned from a library that already does this for Python. But as I was looking at the data here and I was trying to figure out what the heck the values were, remember I mentioned that there is the 6F030000, and I couldn't quite pinpoint to what that actually is until I remember that there's this thing that I learned in college. It's called Little Endian, Big Endian. And if you, again, go to the blog post, read more on it. But the idea was that as I looked at those values, I realized that it's actually not 6F03, it's 036F. It essentially is the length in reverse, right? So it's a different way to represent the length of the packet. And if you look at the packet sequences, it's going to be very, very similar. And then So what this does is for these packets, so 6F03, they actually go together. So while here in this code, you can see them separate, it's bit, mask, length, shifted length, they're actually going together. And you could just as easily just grab them, reverse them, and convert them to int, and you get the length of the data that is being sent. So it's not actually, not 1024, it's 1016, because what I also realized is the first 8 bytes are what's called the header here, right? So it is the consistent part of the packet that is always kind of, I want to say, restricted to what the Stream Deck is trying to do. It tells them all the information about the length of the packet that you're sending, the kind of packet that you're sending, and so on. So the header is the same. And the way that I identified that the header is 8 bytes, again, is there could be a little bit of guesswork, but if we look at Wireshark and is what is actually being transmitted, notice there's a giveaway here. It's called JFIF. And you're like, all right, this is kind of a standard thing that happens when you have a JPEG file. So you can open any JPEG file on your machine, right click, open with, and use something, for example, like Sublime Text with a hex viewer, and you will see this header. And this header is fairly similar, and it always starts with this like FF, D8, FF, E0, 00, and I think there's a couple of other bytes, but it's consistent for all JPEG files. So I looked at that and I said, hold on a second. So does this mean that if I look for this JFIF header, I can actually probably subtract from 1024 the length of the rest, and it's going to be 8 bytes. So the first 8 bytes, 1, 2, 3, 4, 5, 6, 7, 8 are the bytes that are actually representative of the header, and the rest is the content or the chunk of the JPEG. So the second part, and I mentioned 6F and then 0000, is the iteration, right? So the current iteration or the current number of the packet that is being sent. So for example, if this is the first packet, this is going to be 0. It's going to be the second packet, it's going to be 1. It's 0 based. So keep that in mind. Again, once you start iterating and you start inspecting those packets over and over and over again, you will start seeing patterns, and you will emerge with some observations. And similarly, for example, if I look at the set report here that does the sleep part, and I will look at my SDK code as well. So what I did here is set brightness, right? That this is exactly what this does. So remember I mentioned that it sends different packets. So this sends the packets slightly differently because it sets a feature report, right? So this is a feature report. This is not an actual input or output report. This is the third category. But look at the data here. So there's 0308, and as I called out, these are the first chunks that are being sent to the device. This is the header that I looked and inspected and said, okay, this looks familiar. Then I said percentage. This is the second part here. So if I look at the data and I just select just the data, notice that there's that 50. So that sets the brightness. And then there's 00, a bunch of zeros, and 500C, 99, 4E, and there's a bunch of other stuff. I have no idea what that is. And so what I did is I completely skipped over it. So if you look at the SDK here, if you look at this reverse engineered code, it actually doesn't contain any of those bytes. It's just zeros because it still works. And it looks like that data has no concrete impact from what I can tell. I'm sure it does. I'm sure there's a reason for it, but I just did not investigate it. And when I looked at this USB data, basically try to figure out, okay, well, this is how an image is set. This is kind of the data. All I did is then try to formalize this in a C# application using this wonderful library called HID-Sharp that allows you to talk to HID connected units at your computer. I'm not going to say HID device because the D at the end is device. I need to remember that. But that's all it is. And then I just formalize it, and I didn't have to deal with the low-level API stuff. I just use existing HID wrappers. Thankfully, it works relatively easily with it and reliably. And so I just set feature here, and here I just send bytes to a stream that once I open a device, I just send it to a stream, and that's it. That's kind of came from that experimentation using Wireshark with USB PCAP, and that's kind of the methodology. It's a lot of trial and error, a lot of looking at just the regular software, setting a button and seeing what happens, and then trying to replicate that on a device. Thankfully, there's not a lot of barriers in terms of, you know, any kind of certificates or passwords or anything like that with the connected Stream Deck device, because all it does, it acts as a keyboard. It's just a fancier keyboard that's attached to your computer, and luckily we can use Wireshark to inspect the data in it. So this is kind of it. This is an overview of how the reverse engineering worked for the device and how I thought about it. And for more details, check out the blog post that's linked in the description. It goes much more in depth. It even explains some of the binary stuff that I had to revise from my college days. So hopefully that is helpful. And if you find any inaccuracies, anything that stands out and you're like, hold on, Dan, I do not understand that, feel free to leave a comment, send me a note on Twitter or over at my blog. Well, in my blog, we'll still send you to Twitter. So I will see you then. And until the next video.